Okay, so let's look into 4, 6. So the biggest thing in here is kind of solving some exponential equations. All right? And kind of like what we just did up there, where we had a variable in the exponent here. Okay? And how do you solve that? Well, you could use, that was conveniently e, so it had a natural log for the base. And you could still use a definition on this, but you don't have to. You can also take what is commonly called the log of both sides. And so when you do that, you get this. Okay, so then we use our properties of logarithms, and this 2x, you might remember, pops down in front. Okay, so then we have 2x out in front. And then we can just divide by the log of 3. So this idea is maybe a little simpler than using the definition. Here, oh, I can't get up. Get a calculator pulled up here. So let's see. Now I'm just going to take the log of 425 divided by the log of 3. I gotta see which way this works. There we go. Divided by. So I get this. It's good to carry these logarithms out a little bit. So anytime you have a variable in the exponent, such as we did there, one good strategy is just to take the log of both sides. Okay. That exponent thing is going to pop down here in front. That's one of the properties of logarithms I think we had last week. And then just divide it out. So we could have used that strategy on the problem that Dan asked there. When we had the e to the 5k or something, we could have just taken the log of both sides. And in that case, you don't even need the natural log. You can just take the log of both sides and it works out. Or you could use a natural log. So anytime, anything at all, you have even like a fraction. Okay. All you have to do, log of both sides. Anything that's in the variable like that, exponent's in there. Okay. This is always going to pop out in front. So then once that's out in front, then you just got to solve it. It's just a normal equation. Don't let the log thing throw you. Okay, that's it. So anytime you have an exponent in an equation like that, just take the log on both sides. Okay. The other parts of this, like I said, I'll work a couple examples here. Just solving some log equations. So kind of a part 2 to this. So in this case, these two things, these two bases have to be the same. Okay? And this is a pretty simple one, but so as long as those bases are the same, we're okay. So now what we can do is say, now we're going to use the property of exponents in reverse. So we're going to put this guy up here. And since those bases are the same, that means these two things are the same. So now it's almost as if the logs kind of cancel each other out. And we get that. Okay? But the bases have to be the same, or else you can't do it that way. And it has to be a positive 3 because we can't take the log of a negative number. So, yeah.
Shouldn't the negative number be squared before it's log?
Not here in the original equation. Okay, so here's another type. So again, notice that the two bases are the same. Okay, so that's what we got to really got to have that. And all their problems should be that way. So then we'd use the properties of logs again. What happens to the x plus 2 and the x plus 6? Do you remember what that property, what it says that we're going to do with them? Yeah, we're going to multiply them. Okay? So you're going to get this. And we'll multiply these. So whenever we add, we multiply. Whenever we subtract, we divide. Now, you think, well, this looks really dang complicated. So now what you're going to do is use that definition. So this base to this number is equal to here. So base, the output becomes the input. Then we just have to work it out. So we can FOIL this. Okay, so we're FOILing it. It's a quadratic, so we got to set it equal to 0. And then you just got to solve it out. Okay. So we FOIL. We find it. Got this. Move the 5 over because it's quadratic. And then, hopefully, it factors to get that solution. And this one does because we have 7 and 1. I'll pause for a second here. So then our solutions are here. But since we're getting negative solutions, we probably want to check them. So I'm going to run back up here to the top and see if we have any issues. Right, so if we put negative 7 in here, we get negative 7 plus 6. Well, that's negative 1, so we can't take the log of that, so we got to get rid of the negative 7. The other one was negative 1, but that's okay. And it's okay here. So that negative 1's all right, but the other one is not. So we're going to pitch the 7 and go with the negative 1 as our solution. All right, so you kind of have to go back and check them to make sure you're going to get the right. They're both going to work. Any questions on that part? Okay, so we try another one like that. Again, we have an addition. We have this thing out in front. Okay, so we got to think about, okay, we want to try to simplify this into a 1 log. So I know I'm going to have the log base 2. All right. So what's going to happen with this 3? Where's it going to go? So when the 3's out in front, yeah, so this guy over right there. Oops, I don't know why I wrote it like that. X minus 1 cubed. Then we have a plus. So what does that mean in regards to these things? Multiplying. Okay, so it looks like that. So again, this looks pretty messy. But let's see what happens. So here, we want to apply that definition of a logarithm again. So 2, see, you keep using that definition of a logarithm. It's so important in a lot of these problems. And now it's just a matter of just kind of keep working on it and solving it. See, I really don't want to cube this out, because this is going to be a mess. I mean, if I cube that out, it's going to take me a while to do the problem. So as long as I don't have to do that, I'm going to stay away from that. So now how do we solve for x? What should our next move be here? Yeah, let's do a cube root. and then just add your 1 and it's done. So it looked like it was going to be a pretty complicated, particularly with that 3 power, but it really wasn't. We tried to stay away from multiplying that all out, and it worked out for us. Okay? So a lot of these solving log equations are going to look a little messy in the beginning. You're going to go, what the heck? But you just got to use those properties and use a definition, and it all works out pretty well. So I'm kind of looking at the exercises now and seeing if there's some in here that are... Let's try this one out. Okay, so this one has x minus 2, x plus 4, and a log of base a. And so you might get a little bit like, oh, base a, what do we do with that? Well, let's just see what happens, okay, as we work this out. Because it's in the book, so it's got to work out. They all work out usually, right? I mean, if I'd have made it up, we'd be in trouble, but yeah. This is a book problem, so it's probably okay. All right. So again, properties of logarithms. What are we going to do with these two? How can we rewrite that? What's it going to look like? Yeah, log base a of... Right, good. Okay, so again, adding means you're going to multiply. That's that property of logs. Okay, so we have this. These two things are the same. Those are a's. Right? Basically, that means that we can kind of cancel these out. I mean, that's really the way you could think of it, because they're the same. And now it just becomes that kind of an equation. So what may have been something that been a little bit like, oh, I don't know, what are we going to do here? It's really not so bad. It's just working those properties of logarithms, and then we can get into something that we can play with. So then we got this here. It's a quadratic, so we got to set it equal to 0. And again, since it's a book problem, it's going to factor even though hardly anything factors. You just need to make sure you check those answers to make sure that everything works. Okay? So 4 is okay, 4 is okay, 4 is okay because we're getting positives, but -1, right there we have to pitch it. Bless you. So, questions on any of that as far as the solving those log equations? We're good? Okay, let's do one more. Here's where we have one in an exponential. Again. So what was our technique on this? What are we going to do if we have a variable in the exponent? Right, we're going to do the log of both sides. That's going to pop out in front. Going to pop out in front. So here, it's not just straightforward in that we have a number on one side and a variable on the other. We got two variables. Okay, so dividing by the logs isn't going to really help us a whole lot. I mean, it might a little bit. So we're probably just as well to figure out what the log of 3 is and multiply it in here. So you could kind of go like this, I guess. Figure out what that is. Figure out what this is. There's that. Is that right? And then do the same thing on the other side. So I'm just taking the log of 5 and now you can just combine the terms and after it, so. I'll move that one over there. Oops. 6, 4, 0, 3, I think we got there. Yep. Divide that by 1.21, and there's our answer. Okay. All right. So that's kind of how you do those ones. I mean, you know, you're just kind of manipulating the logs a little bit using those properties that you worked on last week. Okay. If I remember right, I think for the most part, most folks did pretty well on those, just kind of working through the properties and sorting stuff out. I think with these, and then otherwise it went pretty well. Questions on any of that then you want to see again, or more examples? Okay, 4.7. Talks about the money part of applying some of this. Okay, some things you've probably done before. Mainly what they talk about here is interest. Okay, and looking at different types of the interest thing. I I think there was a couple of things when we did some of these last term. I had some people get a little bit confused on that part. There's basically a couple different types of interest here. Okay, there's simple interest, as you probably know, and then there's a different interest. There's also an amortized, which most of you are probably familiar with. You know, that would be when you buy a house, you get an amortized mortgage. That's a whole different deal, and it's quite a bit more complicated than what this is. Okay, these are just some interest. You can kind of use some of these formulas to approximate what your like car payment would be, or something like that. All right, although they use some other type of scenarios in that one. So anyhow. Enough of that. So in simple interest, so like this would be maybe if you're loaning a friend or something some money, or a family member, you probably just you always joke around, yeah, I'll charge you interest, right? So this would be like a simple interest sort of way you would do that. If you had, P stands for the principal, by the way, and R is the rate, T is the time, and I is the interest. So, say somebody says, hey, can I borrow a couple $100 or something like that? Okay, so if we're going to borrow a couple $100, okay, then you'd say, sure, but I'm going to charge you, 10% interest on it or something like that, right? And maybe they say, well, pay off in 6 months or something. So, okay, sure. We'll do it monthly, though. It's going to be pretty high. So we're going to go 200, change this to a decimal. Six. And then multiply it. So this is just a perfect example of, see, you almost doubled your money there. Now remember, that's just the interest. So the total is going to be $320. Okay. So that's just simple interest. Most of the time it's not monthly, it's usually in a year sort of situation. Okay. What most interest sort of companies will do, or institutions, is they use what is a compounding interest formula, which looks like this. So this is a little bit more realistic. P is still your principal. R is still the rate. And though is the number of times the rate is being compounded. Of course, T is the time. And here's this, using this formula kind of messed some people up. So here, this one takes into effect the compounding. Okay. So years ago, quite some time ago, credit cards companies would use this kind of formula to figure out their interest, right? But what happened was that they would report a rate of, say, 8%. And what would happen is that at the end of the year, say that they're going to do it 8% monthly, and I'll give you an example of that. So 8% monthly, right, means they're going to take the 8%, divided by 12, and over the course of the year, this would become to the 12th power. So they're applying that interest rate every month, right? Well, then at the end of the year, if you look to see how much you pay, you ended up paying more than 8%. So, you know, people kind of complain and say, hey, they're not telling the truth here. So then they change it a little bit, so they talk about like APR, annual percentage rate. That's where that came from. Okay. So I give you an example kind of how that is. Well, let's just work through this. So one of the things that we have, so let's say we're still dealing with the same situation, right? We're going to borrow the money, okay? Because the guy, you know, your friend says, wait, I can't, that's too much. So, all right, tell you what, you know, I'll go 8%, and I'm going to do it monthly over the course of 1 year, all right? So, how does that work? Well, in this, we're going to do the same thing. So we have A equals 201 plus the interest rate, which you lowered a little bit for them, okay, over N, which is the number of times it's compounded in a year. Since it's monthly, we'd put a 12 there, which is obviously the most common one. And then you'd have 12 and times 1 because it's just over a course of a year. So this is what we've got. Because it's just over the course of a year. So then you just type that in, most likely in the decimals or something, and it's going to spit you out a number. So I'll try it in my calculator because I obviously can't pull decimals up here. So let me see how this works out here. So I get that. Now I'm going to add that to 1. So I get that, and now I got to raise that to the 12th power. So I get that. And now I'm going to multiply that by 200. So that gives me $216 and 60 cents. All right, so that's not the interest, that's the total amount of the loan. So this time, this person's only paying $16 in interest, so they'll probably jump on that one much more than they're going to jump on the simple interest one. All right, so that's your total amount there. Over 1 year, and not making any payments. It doesn't take that into consideration. All right, but what happens is that, again, you're taking this interest rate and you're combining it, so you're dividing it by 12, right? So let's look at this then. If we have 1660 over 200, because we want to check to see what fraction of the interest is the whole principal. So see, that's equal to 0.083 or 8.3%. So that's what the credit card companies were doing, is they were putting that number here, and then at the end of the month or end of the year, they were saying you're only paying 8% when really you're paying 8.3%. Okay, well, it's 0.3%, but it could make a difference, you know, if you had quite a bit of money, right? So then they had to change it and say what an annual percentage rate is. So this would be the annual percentage rate of that particular loan, the APR. Sometimes that's why you see APRs are weirder numbers. Okay. So let's kind of keep playing with this. So we got 200, right? And we'll just stick with the 8%. But what happens if we say, well, we're just going to compound it semi-annually? How does that change the ball game a little bit? So that you're still going to do this, still going to do this, still going to do this. It's just that semi-annually means instead of doing it monthly, we're going to do it twice. Semi means 2, so we're going to go 2, and then this is going to be 2, right? Because it's just NT, and we're still looking at it over a course of a year. So we'll do this one. Raise it to the second power, and then times it by 200. And we have 21632. Whereas that one was 21660. So you're saving this person 28 cents. Again, that's only over $200, so it's not that big of a deal, but okay. And that probably makes sense to you. I mean, if you're not going to compound the interest rate more, it's going to be less amount of money. Now we could go quarterly. Quarterly would be 4 times a year. So they're going to throw some different terms at you. You know, how many times a year. So they actually have annually is once, semi-annually is twice, quarterly is 4, monthly is 12. Let's take a look at daily. And most people think, well, daily, if that's happened daily, then because we're taking this to the 365th power, I mean, man, this really ought to make a difference, right? I mean, that's probably what you think. Well, let's try it out, and then I'll let you try one out on your own here. Oops, I don't want that. So even though you're doing that, compounding that interest every day, you really only made 5 cents more than you did when you did it in a month. Okay. Do you see why? Right. You're just dividing that rate by 365, so it becomes much smaller. Right? And that's why. Okay. So try this out. Put this in decimals, because I'm not sure exactly how my calculator is going to handle it. So let's say we did it same thing, but we're going to compound it every second. All right, so we're going to 200, 1 plus 0.08, but here we've got 365 times 24 times 3,600, and that would be the same thing up here. Try that out, see what you get. Put that into your decimals and see what happens. Let me know what you get for an answer. 216.65.
Stop there at 66.
So it's 216.
6574.
Okay. So it's pretty much the same thing, all right? And we could do, again, you could do the same thing. You could go, you know, milliseconds or whatever, all right? And you can see that this number is kind of starting to flatten out. It's just approaching that 216.65. It just doesn't seem like we're ever going to get higher than that, all right? So that's called compounded continuously. So when you see compounded continuously, then you're going to apply this formula. And back in the old days, we used to just call that PERT, because there was a shampoo named PERT. So it just kind of connected. So it's just PERT. So what does that mean? Well, so here's your amount, right? P is your principal. E is the number E. And then RT is the time. So really all you're doing is taking this part of it, gosh dang it, this part of it here, and this is just simply becoming E, all right? So as the number of times, so as this number becomes larger, then what's happening is this is getting pretty close to E, all right? To the n power anyway. I should include that, all right? So we call that PERT. So how does that work? Well, so then if we were going to do, again, beating the $200 up at 8%, and this is just going to roll, it's never going to stop. So after 1 year, that's what they would be. So let's try it out here. Well, I better do this first, clear. There's my E. .08 E. See how it's 1.08, and we've had 1.08 quite a bit. There it is. All right, so you have different types of, you can do simple interest, which is hardly used, continuous or compounding interest with the different levels of compounding, which is kind of like what car dealers, that's kind of what they do, all right? And then you can have continuous, all right? And that's what they use. And credit card companies kind of do the simple or the compounded interest also, all right? Pretty much a variation of that, all right? Oh, there's one other thing that's kind of interesting that I don't know if many people know. But let's flip this and let's do an investment. So I'm just going to pick $500. Okay. I think like my credit union has like a 3.3% deal right now on a 36-month CD thing. Doesn't seem right. I'm not sure if that's probably. It could be if you guys did it, you might get a different answer because I think like this calculator doesn't do a really good job of figuring things out. Somebody try that in Desmos and see if they get something different.
I got 505.
505? Yeah, it makes more sense. 0.4? Okay. So, the question is then, what if I want to double that investment? So this is what I'm trying to figure out. This is, yeah, that's right. No, this was wrong. I screwed this up. This should be 12 times 3. There we go. I was thinking of income. So that should be 12 times 3. So here, let me do this here. So NT 12T. So what we want to do is figure out how long it's going to take to double it. Okay. So here I have 12T. T is my time. 12 is the time I'm compounding. So I'm just going to solve this little equation. Notice that becomes a 2 because that makes sense because I want to double it. So here, this is a perfect example. So we have a variable in the exponent, right, of this crazy thing, and we want to figure this 2 out. Hang in there, I'm almost done here. So what we want to do is log both sides because that's how we solve these. So this is a good example of where you would apply this logging both sides. Okay? So this doesn't change. This is going to pop out in front. We just got to figure that out. But that's just putting things into Desmos and calculating it out, right? Log 2 divided by the log of 1.03. Maybe even my calculator can do that. Get it out of the... No. Get it out of the way. I don't think it did it. It's probably better you guys do it because I don't. This thing just doesn't. .05. Then I need the log of that. 0.001. Does it turn out to be about 330? I don't think it does. How much?
28.07.
Sweet. Was the answer?
28.07.
That's the whole answer, though? Okay. So this was how much?
28.07.
Is the interest 30% or 3?
Point. It's 3%. I had 3.3, but it would make it 3%.
If it's 30, then it's 277. If it's 30, it's 28.
No, it's not 30. That would be awesome, but if it was 30, I'd be jumping on that, and I wouldn't have to teach Saturday classes, huh? So what is it if it's 3%? Okay, and we'll divide it by 12. What does that turn out to be? Yep, that's what I got too. Okay, so about 23 years is a pretty long time. But what's interesting is there is a rule of 72, they call it. And if you take 72 and divide it by 3, you actually get a pretty dang good approximation for how long it takes for something to double. As long as the interest rates are rather low, the rule of 72 works almost every single time. Okay. So you could have approximated it pretty much by using the rule of 72 when your interest rates are rather low. You know, so when you have like a higher interest rate, it's not going to work. But if we're at 5, 6, 8, somewhere in those, lower than those, you can figure it out. All right. So it takes a long time to double something like that. 3% sounds good, but maybe not so good. But you only started out, didn't start out with a lot of money either, so. All right. That's good enough with investments, I think. You guys were working on the problems. So I looked at the quizzes from last week that you took, and there was a couple of things I think that is worth mentioning. So, before you take your test next week, there was one here that kind of looked like this. And let me get this down a little bit. 2, 6, 3, 8, 4, 10, 5, 14, and H is 4, 7, 6, 9, 8, 15, 10 and 10, 14 and 5. Okay, and the question was to find h of f of x. Okay, some of you might remember this one here. So when you want to do that, what you do is you start with inside here in the f function. So you go to the first number, which is 1. Okay, so 1 is the input, which gives you a 4. So now this output becomes the input into the h function. So you go 1, 4, 4 matches here, so then 7. So then what you would write is you would write 1, 7. Okay, so then you go to the next one, 2. 2 goes to 6. Well, that output becomes that input. So then 2 and 9. And then 3, output or input, output, right there, and so forth. Oh, get out of there. And then 4 is 10. 10 goes to 10. And then the last one is 5, 14. 5 goes to 5. So then the composition looks like that. Okay. So there was a number of people who had stuff, you know, maybe 10, but that it's kind of dismiss it a little bit. So start with the inside function f, right? Go to the first number that's in the input, output, that output becomes that input. That's kind of the definition of a composition, okay? So I saw that one. This one wasn't meant to be tricky, but kind of is, I guess. And if you graph, oh, it was supposed to be find the inverse, if it existed. So if you graph that, you're going to get this. And that does not pass the horizontal line test, which means that the inverse of this graph does not exist. All right. So remember we talked about that. So then if somehow we restricted that domain so it was just this part, then we would be okay to have that part as our inverse, okay? So you kind of have to be careful when you're looking through. That's why I put down there, if it doesn't have one, say it. So if you see, you want to check those graphs to make sure that they pass those horizontal line tests before you go ahead and find the inverse. I think there was one person who kind of picked up on that, but I'm not sure. So I want to make sure that we get that part figured out. So when you do your test next week, you know, check those functions before, unless it specifies that the domain has been restricted. Okay, then you're okay. The other ones that were kind of missed were finding the exponential equations. Maybe I just didn't do a very good job of explaining it or something. But this is kind of key in doing your next activity because that's the first thing that you start with. So 0, 1, 2, 3, 4, and 10, 25, 62.5. This was like 156.25. Anyhow, I said, here's the equation we want to write it in. Y equals A times B dx. A, what does A represent? What does A represent? Right. It's initial value. Okay? That. So you would put that right there. All right? Now B, okay, B, remember we talked about growth factor, growth rate. Okay? This is a growth factor. Okay? So what you want to do to find that is just simply divide these and say, what is that growth factor looking like? Okay? Now in this case it was nice because I made it come out that way. So it was 2.5. But when you do your little activity / project thing, it's real data. So it's not always going to turn out to be a nice number because it's real stuff. So then what you have to do is just kind of average it maybe, or come up with some number that you think represents it. It's not going to be perfect. So don't knock yourself out trying to find a perfect one. But in this case, I made it that way. So then y equals 10 times 2.5 to the x. All right, that's how you would find that equation. Then I gave one where I said, well, here's 2 points. On the, and that's an exponential. Okay, well, here, I don't tell you what the initial value is, so you don't know what it is. All right, so there's actually a couple ways to work on this, but let me show you kind of a slicker way. So here's 4. So 4 is, let me do it this way. So 4 is the first, here we go. So 0 term, we don't know what that is. We know 1 is 4. We don't know what 2 is, but we know 3 is 9. Okay, so we don't know A, right? We don't know B, but we do know that here, that growth factor has been applied twice to get from 4 to 9. So one's here and one's here. So what if we did this? What if we said, well, let's take 9 and divide it by 4 and see what that is. So if I take 9 divided by 4, not 44, 2.25, okay? So 2.25, so we divide 9 by 4, we get 2.25. Now remember, that's been applied twice. So you say, well, wouldn't I divide then maybe by 2? But in actuality, you wouldn't, because if you're dividing by 2, then that would be how much is being added to this. But it's being multiplied. So what we'd have to do is square root it. And it gives us 1.5. So that's my B. So then I could go y equals a times 1.5 to the x. So now all I got to do is find a. You say, well, how in the heck would I do that? Well, there's a couple of ways. One, you could just go backwards here and divide 4 by 1.5 to see what the answer is. Or you could simply say, well, I don't know what it is when time is 0, so I'm going to go y equals a, well, it won't tell me. So I'm just going to go 4 is equal to a times 1.5 to the first, because I do know what this point is right here. And in this case, then I'm just going to take 4c and divide it by 1.5. .6 repeating. So there's my equation. So you could have did it that way. You could have wrote 2 equations. Y equals a times b to the x. So you know that y is 4 when b or x is 1. So you'd have this. And you also know this. So this one you could have went b is equal to 4 divided by a, and then put that into here. And you would have eventually got the right answer. 4 times 4 is 16 times 4 is 64 over a to the third. And then figure it out from there. But you get the same thing, okay? It doesn't change anything. You're still going to get the same answer, all right? Okay, so you could have done it either way. This is kind of a little bit easy, kind of a cooler way of thinking about it. But that's how you would do it. And then the graph one, I gave you what the initial value was. You just had to figure out what the b was, which was just a simple little square root again, or you could set it up with the equations, right? So I wanted to make sure that I went over that, and I recorded it too, so if there's something that you wanted to look at it again to see how to do those, because those are things you're going to see again on your test next week too would be something like that. Plus, it's what you need to do on the activity, so I wanted to make sure we got that covered. Okay, those are the only things that I saw on there that I was too concerned about. There were a couple folks who got confused about this. I'm just going to make some up. So if you're going to do f of g of x, you work inside out. So the g function here is going to go into the f. So this goes into here. F of g of x, g goes into the f function. So when you see f of g, g goes into the f. So then this is going to be 3 times 2x squared minus 1 like that. Okay, and then you should work it out, what you guys did. If it's g of f of x, then the f goes into the g, so that's different. And it becomes that kind of a thing. Okay, and you would work that out. So hopefully that kind of helps a little bit on some of the confusion that there was on that before you take your test next week. Okay, so I got that done. So this section 4.8, which is the last thing in here, there's just a couple things that need to be mentioned. They are just applying exponential growth, okay, or decay. All right, so that's what they're doing. So there's a couple things I want to do that I'm pretty sure is in here. They do some carbon dating problems, which really isn't a whole lot different than any type of growth or decay that's exponential. In this case, it's decay. And they're giving you the equation. They're saying that A sub t is equal to A sub 0 E to the K T. So if I had a problem like this, I would give you the equation or give you at least some data so you could find it. All right, and it wouldn't be too bad. Either I'm going to give it to you, or it's going to be something like what we just did. And I'm going to say, hey, here, here's the initial populations here, and here's how it grows. And you just got to fill in the blanks. Okay. So mine most likely would look like this. There, in this particular assignment, when they talk about decay, they're going to give you the equation, and it's going to look more like that one, all right? So in this case, they talk about half-life, which some of you have probably heard of. That's how they do some dating of archaeological bones and stuff that they find, okay? They use carbon dating, at least they used to. I'm not sure they use that much anymore. But for example, a number 3 talks about traces of burned wood in an archaeological dig, and it says they contained 1.67% of the original amount, okay, of original amount, which isn't much. Okay. Then it says the half-life of this is 5,730 years. And they want to know how old is this tree or whatever it is that's been burned down. So we have this equation. All right. So what they want you to do is use this idea of half-life. Okay, half-life is this. So basically, that is how long it takes for half of it to decay. All right? So if we started out with, say, 100% here, then half would be obviously 50. 5, 7, 3, 0. All right. So what we're saying is that the half-life of this is 5,730 years. Okay. We've got 100% of it originally, but over time we don't have 50% of it left after 5,730 years. So this is another example of where there's an exponent in the, or a variable in the exponent. Okay. So I'm going to divide here first, which is a really good idea because you want to keep that thing pretty simple. Here's our k. So what are we going to do here to solve that k? What's our strategy? Yeah, we're going to take the log, okay? Now, you could use log, but you've got an e, so which log should we use? Yeah, let's just use the natural log, okay? So this, because of properties of exponents, is going to pop right out in front. This is a 0.5. So it looks like that. Okay. Now the natural log of e is pretty much going to just, it's not really relevant because it's just 1. Because you have e to 1 is equal to e. So really you have this. That's why you use the natural log, because you don't have to worry about it. So now I'm going to take my calculator and figure this out. If I got a natural log on here, nope. Now I do. 5 natural log. Why do I have a negative? I bet there's a negative in the formula and I didn't see it. No? Oh, k could be negative. That's okay. Natural log. Ah. Got it. Clear. 0.5. I was thinking that something else that was going to be negative. I thought, well, we're in trouble there, but the k is okay to be negative. So I get a pretty nasty number. I'm going to try it again just to make sure. .000. So I get this e to the negative 4, which means I got to move that decimal 4 times that way. So 1, 2, 3, 4. So I get 0.00012 for k. And now that I know what k is, I can do whatever I need to do. Okay, so now it asks me back to the original question. It was 1.67% of its amount, so I'll put 1.67 here. Now that's percentage, so I'm going to put 100 back here. And then It's the same darn thing that we just did, except now instead of figuring out what k is, I'm going to figure out what t is. Okay, so divide, divide, and then take the natural log. 0.0167. Take the natural log, take the natural log, t, pop it out in front, this is going to go out in front, the log of e doesn't matter because it's just 1, and then we divide. So here we're going to get a negative, and that's okay too. 0.0167 natural log divided by 0.00012. And I get 34,102 for my time. Right? $34,000, 102. 0.8 years. There we go. All right, so there it is. So that is exponential growth decay sort of model, decay with half-life. Kind of crazy process. It's a long problem, but that's really the best way to do it. Any questions on how we kind of did that? It's kind of long. The other one they talk about is Newton's law of cooling. So again, if you think about, so exponential growth and decay has a number of different applications, and one of them is, so if we had something temperature, warm, like a hot drink in the wintertime, and we set it out, it's going to cool. Okay, slowly. Some of them are going to cool a little faster than others. All right, or maybe even the opposite. You know, could happen on a warmer day. Right, things are going to heat up. Okay, so that's all exponential. All right, so there's Newton's law of cooling, which is on page 352. I'm just going to note that here, so you know where it is. Goes like this: U of t is equal to big T plus u sub 0 minus big T parentheses e to the kt. So there again is e. Okay, so see, e keeps popping up in a lot of different things. All right, so what does this stuff stand for? Well, u of t is the temperature. So u of t is the temperature at a time little t. All right. Big T is the temperature of their surroundings. So in other words, whatever it is, like in this room, which feels pretty chilly. The air conditioning is running really well here today. All right. It is. So T is that surrounding temperature. U sub O is the initial temperature. And K is that constant that we're always trying to find, right? So again, you wouldn't have to memorize this equation. They're going to give it to you, or I'm going to give it to you, or whatever. All right, so it would be there. So example number 4 in our book here says an object, so we have an object at 100 degrees Celsius, right, and then they'll put it in a room that is 30 degrees Celsius. So obviously it's going to cool, unless you have one of those really cool hydro flask things that are, you know, seem like they're insulated really well. All right. So then what's to know? It says if the temperature, so if the temperature of this thing was 80 degrees, and that was after 5 minutes, okay, we want to come up with an equation. So that's what we want. What is our equation? So we'll use this thing, and as we did on the other one, it's all about finding that K. So it just becomes more repetition of what we did before, okay? But it's just a different situation. So what would we put here for u of t in this situation? So which temperature am I going to put in there for the temperature at a given time? Well, let's put in 80 because that's what it's telling me. So 80 is going to go there. All right. Big T, remember, is the temperature of the surroundings. What's the temperature of the surroundings? 30. Okay. Plus use of O is the original amount. What was the original temperature? 100 minus, okay, here's big T again. We already got that. We don't know what K is, but we know little t is 5 minutes. So it's just a matter of sorting out everything and putting them in the right spots. All right, so 80 is the temperature after a certain time, which they told us, 80 in 5 minutes. We're trying to find an equation. When we find an equation, we can answer anything they want. So let's work through this. All right, so here's what we got. Obviously, we're going to move that 30 over to the other side. And we can figure this out. And now, see, it just becomes the same thing that we've been doing. All right, it just doesn't change. Only thing that changes is a different application. Okay, still going to do, get it down, divide it, do the natural log, figure out K. Natural log of E doesn't matter because it's just 1. And now it's just a matter of just punching buttons and figuring out what's going on. So I'm going to get rid of this. 5 divided by 7 equals, take the natural log of that. I get a negative divided by 5. So K is negative 0.67. The more I bring it out, the better. I'm going to get a better approximate answer if I have a few more digits on my K. And now I can answer any question that they ask me to. Because once I write an equation, I'm good to go. Let's see, surrounding or temperature surrounding was 30 plus parentheses. Initial value 100 minus 30 times E to the negative 0.067T. There it is. And now I can find out anything I want, okay? And again, if they, like for example, they say, well, how long does it take to get to 50? All right, which happens to be the half-life, right? So I can put that in there, okay? Determine the elapsed time before the temperature is 35. Okay, so I'll put 35 in there. So then I would just throw 35 in here and work it out. But the thing is that you're just doing the same thing. Except this time you're solving for t. So you're still going to go natural log and work it out. It's just now you're finding the time. About 39. Okay, there it is. So again, just do the same thing. Okay, so that's Newton's law of cooling. So I think you'll see there's some examples with that in there where it talks about Newton's law of cooling. There's going to be some examples where it's going to talk about estimating ages of stuff. Okay, those are all problems that are on in the assignment part. Okay. So what I want to do with you, though, here for the next few minutes is talk about logistic growth. Okay? So if you've looked at your activity, it talks about logistic growth kind of at the end. Okay? So it's kind of an interesting little story, actually. So I used to have this simulation for logistic growth that was really good. Unfortunately, it was on the net. It was dependent upon Java, and for some reason it just disappeared. And I could never find it. And I looked and looked and looked. And I about gave up. So I went back last night and I thought, well, I'm going to look and see what I did last term. So I was looking through that, and I just did one more. I thought, I'm just going to try one more time. And I actually found something that was kind of interesting. So I put the link on the DTL site. So I thought what we would do is go to that. We could look at the logistic growth a little bit. And then what I want to do is put some information in Desmos, show you how to calculate a regression equation, which is the last thing you'd have to do on your activity. So I want to try to, I can't record it, but I can kind of say, you can listen to what I'm saying, and then I can kind of write some stuff out. All right, so that's what we're going to do. So I'm going to go to this, all right, and show you how this works. So let's go to your DTL site. And I'll stop when we get to the right spot. Okay, so here's where we want to be at. And I put it in the link or content. Anyway, it's up there. So let's find it. There it is. It should be underneath the materials. So here's growth. This is what it's called. All right. So we want to get to that. All right. So we have a logistic growth model, all right? And what it does is it kind of simulates exponential growth and then what happens over time. So we're just going to launch this. All right, and we get this screen. So here's what this is. They have a red and a blues, so I guess you could kind of do two simulations at a time. all right? This is the number that you start with. Obviously, you can see there's 5 reds and 5 blues. So you can change this to whatever you want. You know, like maybe I'll just change mine to 100 and change this one to 200. But you can put whatever you want in there. Okay, so there's my starting things. This red R is the rate of growth. So this right now it's at 1.2. So, excuse me, it's not the rate of growth. It's actually a factor, all right, which I believe that's what it says it's a rate, but 1.2. I think I tried it at 0.9 and it shouldn't. I'm going to try it and see, but I don't think it's going to grow. So I'm just going to make it 1.2, and maybe I'll make this one 1.4. Okay, again, you can put in some different numbers in there if you want to, all right? And then this value, the K, is what is called the carrying capacity. So what happens to populations is, and I know you can't see this, but I'm just drawing it on here, is that they grow, and you'll see this. So they're going to grow, and then it's going to reach a certain carrying capacity, all right? And it's going to level off, because what happens is, and this really works well with diseases. So if you talk about, like when we, in this winter term, I talked about the measles epidemic thing we were talking about, and I said, well, you know, that's just going to reach a certain amount of growth, and then it's going to level off because of a number of different factors, right? So diseases and sickness, you know, populations, fish in a pond is a perfect example. I mean, you can put as many fish as you want in there, but at a certain amount of time, the food source is going to go away, and the fish are going to start dying, all right? And then another perfect example is that is what happened sort of at Diamond Lake a few years ago, you know, where they had a lot of fish in there, and they introduced some species that was a non-native species, and it killed all the fish off, and then they had to kill off the fish. So the population grew and grew and grew, and then all of a sudden these fish started dying off because of this population of species that wasn't supposed to be in there. So there's many different examples of logistic growth. So if we go ahead and hit this go, oh hey, maybe I'll make my carrying capacity just a little bit bigger here. So I think I'll make this like 600. Oops. Just for the heck of it. Now, I think I can get it close to 600 by doing this. That's good enough. And I'll make this at 500. Oh, I started out too. Maybe I'll make it a little higher. There we go. Now I'll just go, all right? And what it does is it just simulates this growth. So you can see all these things happening. The pink ones, I believe, are the things that are birth, and then the X's are the things that are dying, all right? And it kind of keeps track of that here. But what's happening is that this population, and you can slow the speed down if you want, okay, is now starting to level off. And it talks about how the growth here, the growth rate, okay, boom, 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 and then what happens is it kind of levels off, starts to go back down, because obviously you can see if that was a pond, you're eating way too many fish, and then there's food sources is going away, right? So then the growth changes. And this is a per capita growth. So this is kind of a cool little simulation of what happens in logistics, right? So I'm just going to stop this, all right? So here, right? Here's what's happening, okay? And if you change the numbers, okay, so if we go back and change these, we can change it to something else, all right? Maybe I want to change this. Let's try 0.8. I don't know. Let's see what that does, all right? Slows the growth down a little bit. Here, let me speed it up some. Even though, so that probably is a rate. The blue one, you can see reaches that. And so does the red one, and eventually gets there, even though its growth factor is quite a bit smaller. So it's kind of an interesting little model on how exactly how that works, all right? So what I wanted to do was, I thought, okay, this is kind of cool. And I thought, well, can I show them how to find a logistic equation that models this? And I found out that I could. So, like for example, let's say I pick the red one here, all right? And what it does is it gives me population over time. So, for example, let me find a mark. So, for example, I got 0 and we started with 100. Okay, and then at 3, we had 104. We'll just say 104. Okay, then I'm going to kind of move along here a little bit, not quite that fast. Man, it just takes off on me. Bump it down just a little bit. Come on. I'll take 13, I guess. Okay, and then I'll go to get 27, that'll be all right. And 141. And then let me go up to here. Something in the 30s would be good, 33. And I got 152, I'll just round it up. And then if I go into the 40s, 43, 170, and let me get into the 50s here. So I get some representation there. Oh, 63, I'll just take that. And 2. Okay, now I'm going to shoot it up a little bit here. 3 and 331. I'm going to shoot it up a little bit more. 139 and 393. I'll just say, and then I'm going to do a couple more here. 176 and 467. And then I want to get one where it kind of levels out. 219 and 530, we'll say. And then let's go with one more over here. 282 and 578. Okay, so I just kind of randomly got some points. All right, so now what I'm going to do, I'm going to go back into Desmos here. Okay, and I'm going to get a new graph. So like if this is so here's my data from my little activity thing. So I'm going to go plus to get a table. Okay, your table is already there. 0, enter, 3, 13, 27, and 33, and 43, and 63. This is stuff that's not in our book that probably should be, because this is kind of cool what this does. And 139, 176, 219, and 282. So there's my time, and now I'll put these populations in. So 100 and 104, 118, 141, 152, 170, 213, 331, 393, 467, a couple more here. 530 and 578. Okay, so now I have some population here. All right, and I don't see a graph because obviously let me change this so you guys can see it. Okay, 0 to 300, 0 to about 600. We should see it. Okay, so there it is. All right, looks pretty linear. So what I want to do now is, okay, so I have a logistic equation type that I could use. All right, so I want to switch back to this for just a second. All right, so I made up I have some data. All right, 0, 3, 13, 27, so forth, 100, 104. Again, I'm just kind of writing this out so that the people can look at this later. 63, 213, jumping around a little bit, 139, 393, okay, 282, 578. Okay, so then there's my graph, all right. So I have a logistic that goes y equals c, and I think what I did was I had 1 plus a times e to the kt. I believe it was that. Okay, so then c is the carrying capacity, right? So then, okay, what we did was I said, okay, well, you got to come up with a carrying capacity, right? So maybe we guess that our carrying capacity is about, well, 600, 700. All right, it doesn't really matter. So, okay, now let's use that information and pick the original value. So that would be 100 here equals 700, and then 1 plus a times e to the k times 0. Well, what happens is that this is 1 because anything at 0 power is 1, and you get something like this, okay? And you can find a. So once you find a, then you're all set. You have your 1 plus whatever a turns out to be, e to the kt. And then once you know a, right, you can go ahead and figure out what k is by picking another value and doing the same thing that we were doing, you know, natural log and la-di-da. But what I wanted to show you was how to find a regression equation, which is the last part. So I'm going to jump back into here. Okay, I can pull that back up too if you want to see it. And here's what we're going to do. So we're going to click down here, and we're going to go y1. So y1 is the title of that column. So I'm going to go y1 equals. All right, now I'm going to put a C for carrying capacity, C, all right, divided by parentheses 1 plus A is my constant, okay? I'm going to go back to this. 1, I'm going to put a times here because I think I want to do that. E, see how it knows what E is, to the, and then I'm going to put a K, all right, times X, oops, no, see, I got to back that up. You got to make sure you put a parenthesis here or else it doesn't work. Times X1. What's up? Yes, I did. Maybe Because it should find, oh, dummy me. This shouldn't be an equals. This has to be a tilde. So tilde is this guy right here next to the brackets underneath the N and the B. All right, it looks like that. Okay. So what happens is that it goes through this mathematical calculation and estimates what it thinks is best for A and C. All right. So here is the parameters. So it says that the carrying capacity should be about 611, tells you what K is, tells you what it thinks A is. And if you look at this, that's a pretty dang nice fit. Okay? I mean, that's good. All right? But you got to remember that this data was modeled. So, I mean, the model uses the same kind of equation to come up with the stuff in the first place. So it's not like it's real stuff like what you have. But it's going to be a pretty good fit. So when you're doing yours, and you get down to number 7, question number 7, here's how you would do it. Okay, you type Y1 because that's your data. Tilde C, A, and K are your constants that it figures out for you. All right. So I wanted to make sure I showed you that, so that you could do it when you get to that point on your little activity. Right? It's really pretty slick. And I'm writing it right now on my tablet here so that if somebody, hopefully they got the voice part of it and they kind of see what I typed into Desmos to get it. And it will figure out what those are, and it will graph them, okay? And you'll get a pretty good idea of what. So you'll come up with an equation, and you'll probably type it in and go, that's not real good. But then use this thing, and it'll do well for you. Okay. So I wrote it. There it is. So if you want to see all the other stuff I did, it's right there. All right. So I hope that helps. I hope that helps. So on the activity it says, look for the recording. Well, this is kind of it. All right. Because I can't really do it here because I don't have access to the internet. So that's it. That's all of 4.8 that I wanted to show you. There'll probably be, there might be a logistic question on the test, but it'll probably be not quite like this because this is quite a bit more involving, and that's why I gave you the activity to figure that out. So I hope that helps you. Questions on anything? Maybe I have a lot. Okay, so I'll put the